hate this. Or how much you love that. I like it. I know, we're all math nerds. We like it. Don't tell anybody you like finding the derivative by the definition. Well, if you like finding the derivative by the definition, then you're going to like the shortcut even better. This was pretty darn ugly. I will confess that I have cried over calculus, and that was probably one of the nights that I did.
This is a love-hate relationship?
This is a love-hate relationship. I totally get that. Let's look at something that, you don't have this printed, it's fine. Don't copy it down. We're just talking for a minute. Let's play like that. You gave me this for last night's homework and asked me to find the derivative. Well, by the definition, which is the only thing I knew last night, I would have said the limit as h goes to 0 of f of x plus h minus f of x divided by h, because I have that memorized now. If nothing else, I have that memorized. And then I would have said that's the limit as h goes to 0 of x plus h in the place of that x plus h in the place of that x plus h in place of that x. Here's f of x plus h, and there's minus f of x, and that's over h. That made you groan, right? Oh, it gets worse. I have to multiply x plus h times x plus h times x plus h, and I get that.
Oh my God.
Now, I had a lot of fun typing this. I'm proud of myself for having that type. I multiplied that. I multiplied x plus h times x plus h, and then distributed the 2. I distributed -3. I distributed -1. That's what I had. And then I combined like terms, and that's what I had. And then I factored out an h, and that's what I had. And then I canceled the h's and had that. And then I let all the h's be 0, and I have that. All of that work just to get the derivative of that function. And it's not even a log function or a trig function. Heaven forbid that that had been cosine cubed plus 2 cosine squared minus 3 natural log of x plus 5. That's not the point where I almost became a PE major.
I would probably cry.
Yeah. You know how spastic I am. Yeah, that's funny,
That's
me
the point
becoming
where
a
I would
PE
just
major.
Probably close the book and say, nope, that's enough for tonight.
Okay. Let's look at this function and what we very painfully found out the derivative was. And if you've ever had calculus, you can answer this question, because we need everybody to have their own aha moment. Okay? What could be done to that x cube that would make it become 3x squared? Have you ever seen it before? You've seen it. Be quiet. Miss Kayla, you've never seen it, right? You're just going to lob this ball out of the park. I think I mixed some sports metaphors there. You don't lob out of them. Oh, never mind. Kayla?
So you know how we found the derivative of x squared is 2x? Just bring down the 3 in front of it, and that'd give you 3x squared. Right? No.
Maybe. Let's see. Kayla, you said the derivative of x squared was 2x, so you brought the 3 out in front of the x, and then...
That'd leave you with the square.
Okay.
That's a guess.
Okay. Well, does that work in the second term? What could we do
2
to...
times 2 is 4, and that would give you an x.
Okay. That seems to work. We're going to call this Kayla's law for calculus. Kayla is seeming to say you can bring the exponent out front, that's 3x squared, or 3x, and then subtract 1 from the exponent, so x cubed becomes x squared. And then with the second term, when you bring the 2 out front, you have to multiply it by the 2 that's already there. That would give you a coefficient of 4. Subtract 1 from the exponent, and sure enough, it's 4x. What about this minus 3x? What's the exponent of the x in that situation? 1. And so does Kayla's law work on that term? If we multiplied 1 times -3, what would we have? -3. And if we subtracted 1 from the exponent, what would we have?
X to the 0.
X to the 0, better known as 1, and negative 3 times 1 is just negative 3.
What about the
And yeah, what about the 5? I don't know. Well,
It's already at 1. Or, no.
that 5 is, yeah, I don't want to do that. Remember, let me think what problem. The limit as x goes to anything of a constant, no, that's not going to work. Okay, let's forget the 5 just a minute. We'll come back to it, but let's forget it for just a minute. I know. If we're taking the derivative term by term here, then f prime of x when x is 5, that's the slope of the tangent line to the line y equals 5. What does the line y equals 5 look like? Not just straight, but horizontal line. What's the slope of a horizontal line? 0. What's the derivative of a constant? 0, so I could put a plus 0 on there and wouldn't change the problem. So it appears to me that, I'm going to rename this. By Kayla's law, it seems like what Kayla is saying is, why don't we just bring the exponent out front, subtract 1 from the exponent. Bring the exponent out front, subtract 1 from the exponent. Bring the exponent out front, subtract 1 from the exponent, and the derivative of a constant is 0. Holy cow. Kayla, I think you should get a Nobel Prize for that. That is fantastic. Calculus students of America love you. Mr. Warren.
Can I just throw something out real quick about that
please.
plus 5?
Uh-huh.
If you think about what that plus 5 does to the graph, all it's doing is shifting it, and that wouldn't change the slope.
That's a
So-
beautiful point. Yeah, and that's never crossed my mind, but that's absolutely right. That plus 5 on the end is just shifting the graph up 5. It's not affecting the slope of anything. So that's another reason that you don't have the 4th term there.
Well, the reason why I did that, because I remember the reason why I was kind of guessing it was because last time on the homework, I was noticing the homework.
Good for you.
The reason why I noticed it was because you gave us a hint yesterday saying there's an easier way to do it, and I was trying to
And
figure
you
it out.
started looking for the easier way, and Kayla's law just kind of came to you. Oh, I love it. That's the most fabulous shortcut in all of mathematics. Unfortunately, it was already patented. I'm sorry. There was a power rule long before there was a Kayla. And the power rule says, bring the exponent out front, subtract 1 from the exponent. So if the function is x to the 5th, the derivative is 5x to the 4th. It also was a rule, long before Kayla, that the derivative of any constant is 0 because a function which is a constant is a horizontal line, and a horizontal line has slope 0. And a special case of the power rule is that the derivative of x is 1. Again, if you had the function is just x, and you brought that exponent out front, you'd have 1x, and then when you subtracted 1 from the exponent, you'd have 1x to the 0. Well, that's just 1. And also, the slope of the line y equals x is 1. So 2 different ways to think about why this special case is true. The derivative of any plain old x is just 1. The constant multiple rule says if you have the derivative of a constant times a function, you can just keep up with the function, or keep up with the constant and take the derivative of the function. For example, if you have 5x cubed, you can just keep up with the 5 and differentiate the x cubed, and then 5 times 3x squared is 15x squared. The sum or difference rules is what allows you to find derivatives term by term. if you have the derivative, or f of x is 3x squared and g of x is 5x, then f plus g of x is 3x squared plus 5x, and the derivative would be 6x plus 5. You can take derivatives term by term. Now, let's stop there and do a few examples. From page, what? 136. First few, the first couple, I'm not even going to write them down. Number 4, if the function is negative 9, just the constant negative 9, what's the derivative? 0. Because that's a horizontal line, and the slope of a horizontal line is 0. What about number 6? If the function is y equals x to the 16th, what's y prime?
16x to the 15th.
16x to the 15th. Now, how do we apply that power rule to number 8? Y equals 1 over x to the 8th.
Change it to x to the negative.
Write it as x to the negative 8, and then bring the negative 8 out front, and subtract 1 from the exponent. Negative 8x to the negative 9. What about number 10? How could I use the power rule on that?
Change that to a fraction x.
Change it to x to the 1/6. Bring the 1/6 out front, subtract 1 from the exponent. Y'all are going to get better at fractions than you've ever been. You've got to be able to subtract 1 from a fraction without grabbing your calculator or it taking you half a day. All right? It's supposed to be easy. Number 16. Can you imagine last night finding the derivative of that by the definition?
Which one?
Number 16. It would have been ugly. But now you know that derivative just by glancing at it is what? Derivative of 8 is, we'll just say, derivative of 8 is 0, and the derivative of negative x cubed is negative 3x squared. And number 18, look how easy this is. What's the derivative of number 18? 6x squared minus 8x plus 3. This is the easiest day of my life. I'm ready for something different. I need to be challenged here. Few things you just have to memorize, but you memorize them by doing so many problems it just gets stuck in your head. It's not like you sit down, with flashcards. You just do a lot of problems, and very quickly you learn the derivative of sine is cosine, and the derivative of cosine is negative sine. Just got to remember that. So if the function is 2x, the derivative is 2 cosine x. And if the function is x plus cosine x, what's the derivative of this x? 1. And the derivative of that cosine x? Negative sine x. And the derivative of the exponential function is the exponential function.
You can't derive.
Now, no, you can derive. That is the derivative. And we could do it by the definition, but I'd rather spork my eyes out.
So
I'm just going to trust Mr. Swakowski here that the derivative of e to the x is e to the x. Yes, ma'am.
So the derivative of cosine is sine and not secant.
Derivative and reciprocal are not even related to each other.
Okay, I get it now.
Okay. So if the function is sine x minus e to the x, what's the derivative of sine x? Cosine x, what's the derivative of e to the x? E to the x. All right. Let's keep going now that we have a few more things memorized. Number 20. What's the derivative of the first term? 3t squared. Derivative of the second term?
2t.
The derivative of e to the t is e to the t. So this is 3t squared plus Same old 2e to the t.
Two doesn't affect two.
The derivative of a constant times a function, just keep up with the constant, take the derivative of the function. So keep up with the 2. Ooh, what just happened here? Keep up with the 2 and take the derivative of e to the t. What about number 22? Pi cosine t. What would that derivative be? Almost, except for the derivative of cosine is negative sine. This pi is a constant, just like that 2 is a constant. You just keep up with the pi, and the derivative of cosine t is negative sine t. So negative pi sine t. What about 24? What's the derivative of 7?
It would just be cosine x.
The derivative of 7 is 0. Okay? Now, that's different. Why on number 20 did I say keep up with the 2, but number 24 I said don't keep up with the 7?
That's because it's multiplied.
This is 2 times a function. If you have a constant times a function, keep up with the constant and just take the derivative of the function. But that's not what's going on here. This is derivative of a constant, and the derivative of a constant is 0. So that's 0 plus what? Cosine x or just cosine x. Number 26, what's the derivative of 3/4 e to the x?
3/4 e to the x.
Same old 3/4 e to the x.
Minus.
What's the derivative of 2 cosine x?
Negative sine. Or
Negative 2 sine x. All right? Now, I wish the whole rest of the semester was going to be that easy and we could just, look at the problem, write down the answer. Of course it's not. If that was all there was to calculus, then you wouldn't have heard nightmares about calculus.
And there'd be more engineers.
And there'd be more engineers in the world. Back to the handout. A trick to watch out for is figuring out how to write the function so that you can use the power rule. When we had 6th root of x, somebody said, well, we could write that as x to the 1/6. And that works. We could use the power rule then. We had 1 over x to the 8th. Somebody said, we'll just write that as x to the negative 8. And then you can use the power rule. That's very often the trick that we need. And number 28 through 68, let's keep going, and maybe it's a good time to start writing stuff down. Page 136. Start writing stuff down and run out of ink. Section 3.2, page 136, number 28. I have to write that as just a constant times x to the power. That's the only way I can use the power rule, if I just have a constant times x to a power. How could I rewrite number 27 that way? You know what? You're trying to apply properties of logarithms in a problem that doesn't even have logarithms in it. Yeah, you could write that as 4/3 x to the negative 2. Now, don't keep going with this equals and apply the product rule. Don't write down what I'm writing down unless you're going to cross it out and put a big old wrong on it. Do not keep going here and say negative 2 times 4/3 is negative 8/3. Subtract 1 from the exponent. Why is what I have written incorrect?
That's not the actual.
I'm saying that this equals that. Is that true? Those don't equal each other. That's not just rewriting y. That's what the derivative is. So your notation here is important. Don't go y equals blah and differentiate it and keep calling it y. That negative 8/3 x to the negative 3 is not y, it's the derivative of y. And then we're going to stick with our old beloved rule that says don't leave negative exponents in your answer 99% of the time, and then we'll find that one exception when it happens. But how could I rewrite that so that I didn't have negative exponents in my answer?
Negative 8 over x to the third.
And where did the 3 go?
Oh, sorry, 3x to the...
Negative 8 over 3x cubed. So far, so good? Harriman? Harriman. Woohoo! Yay! Are you good?
Yeah.
Is there only one person in Harriman?
No.
Okay, just checking. What about after these 3 problems where we're rewriting the function and then we're differentiating the function and then we're simplifying our answer? That was number 28. What about number
Oh, that's not good. Can you hear us?
Sweet, let's leave.
Hello? Does anybody know sign language?
Somebody go up to the thing, camera.
Like that.
Someone go up there and like.
Right on the board.
Yeah, right up
Yeah.
there. We cannot hear you.
Oh, yeah.
Really, really, really big.
Wow. I got this.
Just try to
I think she was looking at us.
You can't.
You can't read it.
She does say. Zoom in with the camera.
Okay.
She thinks she did okay.
Maybe she can hear us. But
We
she can't
cannot
hear
hear. You.
Okay. Should have run Mayday. Leave. That's disappointing. I was excited to hear the derivative of that. I think it was
right when they went dead?
Oh, we're good. We can hear you.
I think they're good now. They're sad that you fixed it, but thank you. Okay, I will. Thanks, bye. All right, Miss Kathy's magic finger fixed it. No, the answer is no, you can never leave when that happens because it's easy to fix. Can y'all see what you need to see, or does someone need to go up to the front and press student camera?
We need Elmo. Yeah. No.
No, we need Elmo.
Okay.
There we go.
Got it?
Yeah.
Okie dokie. That was fun. So when you write that in the form constant times x to a power, what's the constant going to be?
Pi over 25.
Pi over 25, x to the what?
-2.
Well, that x is in the denominator with the exponent of 2. So when you write it beside the constant, it's going to have to be x to the negative 2. Have we done any calculus yet? No, we have not. That was just rewriting the function. Here comes the calculus. What's the derivative of pi over 25 x to the negative 2?
2 pi over 25 x to the negative 3.
Negative 2 pi over 25 x to the negative 3. But I'm not going to leave negative exponents in my answer, so I would write that as
-2 pi over 25 x to the 3rd.
beautiful. Harriman, is that good?
Yep.
Alrighty. I'm not going to write down number 32. Just let me ask you, how could I write 4 over x to the negative 3 as a constant times x to a power?
Wouldn't that be 12?
No, you're doing calculus. I'm just asking the algebra question.
Oh.
How could you rewrite that as a constant times x to a power?
4
No.
4x.
It's just 4x cubed. If you have x to the negative 3 in the denominator, when you take the reciprocal, you're going to have x to the positive 3 in the numerator. There is not a process in math that causes you to take the reciprocal of an exponent. Taking the reciprocal of the base changes the sign of the exponent. All right, let me ask you, we'll write down one of these in just a second, but starting out with the easy ones, 33 through 40 say, find the slope of the graph of the function at the given point. Put those instructions in non-calculus. Well, no, you're still going to have to use calculus words, but what does that tell you to do? Find the slope of the line or the curve at the given point.
Take the derivative.
Take the derivative.
Plug in your x.
And then substitute your x into the derivative. The derivative gives you a formula for finding the slope of the tangent line at any point. So I'm giving you a point and saying, find the slope of the tangent line here. All right, 33, 34, 35, those are easy. Let's do 36. Don't start applying the power rule where it doesn't belong. It's tempting just to bring that 2 out front and then subtract 1 from the 2, but the power rule only applies to x to a power. Is this just x to a power? No, it's not. How could I write it as a sum of terms of x to a power? I have to multiply it out and then distribute the 3. So that's 25 minus 10x squared, or 10x plus x squared. And then I could either leave it in this form or distribute the 3. If I leave the 3 undistributed, what do I do when I take the derivative of that function? Keep the 3 or lose the 3? That's a constant times a function. You keep the 3 and differentiate the function. What's the derivative of that function inside parentheses?
Negative 10 plus 2x.
Right. Negative 10 plus 2x. because the derivative of x is just 1, negative 10 times 1, and the derivative of x squared is 2x.
Would it be wrong to distribute the 3?
Let's see if we'd get the same answer if we did. That would be 75 minus 30x plus 3x squared. What's the derivative? I said 3x squared and wrote 32. What the heck? What's the derivative of 75? 0. What's the derivative of negative 30x? Is that the same thing we have right here? Yeah? And what's the derivative of 3x squared? 6x. Is that the same thing we have right here? Yep.
What do you then 25?
The derivative of a constant is 0. I just thought of a caution I could write for you. I think the best way to write it. If the function is 3x squared, and I just want to differentiate the x squared, what do I do with the 3? Keep up with it or lose it?
Keep up with it.
That's a constant times a function. When you have a constant times a function, you keep up with the constant and then just differentiate the function. However, is that the same thing? No, it's not. When you take the derivative of just a constant, what's the derivative of that constant? 0. And the derivative of x squared is 2x. So that caution was to illustrate when to keep up with the 3 and when to lose the 3. I don't even like using those words in a math class. You never lose anything. But you can say the derivative of a constant is 0, but the derivative of a constant times a function, you have to keep up with the constant when you differentiate the function. All right, let me give you another just rule of thumb. You know, rule of thumb applies 90% of the time, and then there are going to be those oddball scenarios. But because of what's coming later, 99% of the time, the derivative is going to be written factored as completely as possible. So maybe in the back of the book, they'll have this, maybe they'll have this, or maybe they'll have that.
Yeah. That's what I would probably.
The reason that in the back of the book, wait, something's wrong. What's wrong? Oh, nothing. That's right. This is 6x minus 30, and that's 6x minus 30, so same thing. But the reason that in the back of the book the answer is usually factored as completely as possible is one of the big things we'll be doing the rest of the semester is setting the derivative equal to 0. You remember what was special on my favorite polynomial yesterday? Those points where the derivative is 0. What was special about those points? There are high points and low points. And very often in calculus, that's what we're trying to identify, those high points and low points. So if we're going to end up setting a derivative equal to 0, then it would be helpful to have that derivative factored as completely as possible. In this section, I honestly don't know which one of those 3 answers is in the back of the book. But good rule of thumb, might as well start it now, factor your derivative as completely as possible. All right, that was 36. Let's do something, number 38. I said, I got excited, but I'm not going to do your odd problems for you. What's the derivative of that theta right there?
It's just a constant.
It's just like x. The derivative of a constant is no. It's not. You said it's like a constant. It's not a constant. It's just like it's a variable. So it's like taking the derivative of x. The derivative of x is 1. All right? So that derivative would be 4 cosine theta minus 1. All right? Actually, we didn't finish number 36 because the directions didn't just say find the derivative. The directions said find the slope of the tangent line at the point, what was point on 36?
5, 0.
At 5, 0. So you could say f prime of 5 would be 0. So what does that tell you is happening to the graph of this function at 5? It has a horizontal tangent line. The slope of the tangent line is 0. It's a high point or a low point. You know from algebra that that's a concave down parabola scooted up 5 and then made more narrow because of the 3. But it's a parabola and its vertex is at 5. Well, the vertex would be a high point, and at the high point, the slope of the tangent line would be 0. I'm not trying to make problems harder than they are. I mean, this is all that you had to do on 36. Say the slope of the tangent line at 5 is 0. I'm just telling you what's coming in the future, and whatever makes the derivative 0, that's going to turn out to be important. Because one thing that engineers, one thing that chemists, one thing that investors want to do is find out what maximizes my profit, what minimizes the pressure, what minimizes the cost, what maximizes the strength of a, yeah. Okay, let's keep going. Number 38. Find the slope of the tangent line to that graph at the point pi 7. Now, if they hadn't given me the 7 and they just said find the equation of the tangent line, but all they gave me is a pi, I would think, but to find the equation of a line, I have to have an x and a y. If they only gave me the pi, where would I get the 7? Put the pi into the original function. What's cosine of pi?
1.
Negative 1. Negative 1. What's negative 2 times negative 1? 2 and 2 plus 5. That's where the 7 comes from. All right? So they're telling me to find the slope of the tangent line at the point pi 7. I'm going to say the derivative of that function is what?
2 sine t.
Because the derivative of cosine t is negative sine t. Now, if you don't need to write this step down, it's absolutely fine. I just don't want anybody to be confused when they get home tonight. Where did the negative go? That's a positive 2 sine t because the derivative of cosine is negative sine. And then what happened to the 5?
Is a constant.
Derivative of a constant is 0. You could put plus 0 there if you wanted to. All right, have we done what the directions ask us to do?
No.
Not yet. We have the derivative, but it asks us for the slope of the tangent line at the point pi 7. So then what do we need to do?
Plug in pi to your derivative.
Substitute pi into the derivative. The slope of the tangent line at the point pi 7 would be substituting pi into the derivative. What is 2 sine of pi?
0.
So what does that tell you happens to this graph at pi? At the point pi 7.
As it's not.
It's a high point or a low point. I don't know which one, but if it's what makes the derivative 0, it's a high point or a low point. All right? One more with an E in it. Number 40. Let's play like they only gave me the x equals 1, and I needed the y for some reason. How could I find the y? Put 1 into the function. -4 times e to the first as an exact answer, y'all need to practice your exact answers, is what? -4e. Not 12 point something something, but -4e. Really, that was given to you in the book. I just made you work for it. What is the derivative of that function? Same thing. That's a constant times e to the x. Just keep up with the constant and take the derivative of e to the x. Well, the constant of e to the x is e to the x. And so how do I find the slope of the tangent line at that point? 1 into the derivative.
Which is the same.
That's the same thing, yeah. -4e. When you're trying to find the y on the graph of this function, you substitute the x into the function. But when you're trying to find the slope of the tangent line to the function, then you plug 1 into the derivative. You need to be more precise when I know y'all talk out loud to yourself at home because that helps you understand math better. Play like you're tutoring somebody else. When you're talking to yourself at home, don't just say plug in the 1. If you say plug in the 1 in your homework, then on the test you're going to say plug in the 1 and you're going to go, ooh, where do I plug in the 1? So go ahead and be saying to yourself, substitute 1 into the function. Substitute 1 into the derivative. Use the right words just as if you were tutoring someone. Who knows, you might be tutoring someone someday. All right. I see something different. Look at number 44. Other than memorizing the derivative of sine and cosine and e to the x, other than those 3 things we have memorized, we really only have one rule, and that's the power rule. Does the power rule apply to this problem? Is it just a constant times x to a power? No. Can I figure out how to write it so that it's a constant times x to a power? How?
X cubed minus 6 in parentheses times, you would need the parentheses, and then times that by x to the -2nd.
All right, that's absolutely one way to do it, absolutely fine. You could write x cubed minus 6 times x to the -2. But if you did, would you be ready to use the power rule yet? No, but I'm only one step away. What else would I need to do? Well, it's not really fold because it's not a binomial times a binomial. It's just distribute. Distribute x to the -2. When I multiply 2 expressions with the same base, I add their exponent, and then make sure you distribute completely.
Why did you distribute?
Because I couldn't use the power rule until I had a sum or difference of terms, and all the terms were of the form constant times x to a power. This wasn't constant times x to a power. This is a constant times x to a power. That's a constant times x to a power. For the very same reason, on a previous problem, like number 28, Sarah, we had to write that 4/3 x to the -2. Same thing. We need a constant times x to a power.
36, we left the stuff in the parentheses.
Ooh, let's see. In 36, we left stuff in the parentheses because that was a constant times a function, This is not a constant times a function. That's a very good point you just made. If I have a constant times a function, I can just keep up with the constant and differentiate the function. But that's not what this is.
So you have to have a constant times a function to a power.
But you know, I don't know if I've thought that some previous semester or not, but that was a really good point you just made. Why do I have to distribute the x to the negative 2 on number 44, but I didn't have to distribute the 3 on number 36? That's a good question. The answer is because 3 is a constant and x to the negative 2 is not a constant. All right. Warren, I had thought about doing that a different way, and both ways are just as good. I was thinking about dividing that x squared into each term. X cubed divided by x squared is x to the first. Negative 6 over x squared is negative 6x to the negative 2. So we don't have to do things the same way. We should still get the same answer.
Yeah, that's a bit short. It just makes, for me, it just helps if I write out anything that's like that as a negative exponent.
Absolutely fine. Good. Perfect way to do it. All right, have I done any calculus yet? No. This is still just the function. Don't keep going and differentiate on that same line. Say, all I've done here is rewrite the function. Now I'm ready to do the calculus. The derivative of that function, what's the derivative of x? 1. What's the derivative of negative 6x to the negative 2?
12x to the negative
12x to the negative 3. And because I'm not going to leave negative exponents in my answer, I'm going to write that as 1 plus 12 over x cubed. Um, 46, I'm not going to write it down. Do the same thing. You could either write that x in the denominator as x to the negative 1 and distribute it, or you could just divide each term by x and write that as 2x minus 3 plus x to the negative 1, and then differentiate. On 48, would I have to distribute that 3x or not?
You don't have to.
Yes.
Or do you?
No.
You don't have to.
Actually, there's
because
I have to distribute the x. I can distribute or not distribute the 3. The 3 is a constant. I would probably go ahead and distribute the whole 3x, but you at least have to distribute the x, because otherwise you don't have just a constant times a function. You have the product of two functions, and we're going to come to lovingly know that as something that we need the product rule. There's a rule for differentiating that, but the easiest way is write it so that it's not a product.
Yeah, I try to change things as much as possible.
Yes.
I try to not use either one of those rules.
Okay. Number 50, can I use the power rule as is?
No.
No, but I could rewrite that as x to the 1/3 plus x to the 1/5, and I'm going to get good at fractions. Let's do 52. Do I need to rewrite that in any way, or am I ready to use the power rule? Yeah, it's already a constant times t to a power. A constant times t to a power, just a constant. I can use the power rule. F prime of t. What's the derivative of t to the 2/3?
2/3 t to the negative 1/3.
You need to be able to do 2/3 minus 1 in your head. 2/3 minus 3/3 is negative 1/3. What's the derivative of t to the 1/3?
1/3 t to the negative 2/3.
1/3 t to the 1/3 minus 1 is negative 2/3. What's the derivative of 4? 0. Don't need a plus 0 at the middle, or right there. I suddenly need to check the answer in the back of the book, because if we're going to leave it like that in tonight's homework, it's easy. If it's not like that in tonight's homework, I need to show you what to do. So let me just check that answer. Oh, well, I can tell by looking at the answer to maybe 53 how they're going to write the answers in the back. Yeah, 51. This is 3.2, number 51. Looks like 52. 3.1, 3.5, 3.2. All right, 3.2, number 51. Yay, we're not going to have to learn that today. It's coming. We'll deal with it another day, but in tonight's homework, all you're going to have to do is write that as 2 over 3t to the 1/3 minus 1 over 3t to the 2/3.
Can I ask a question?
Yes.
Real quick?
Mm-hmm.
If you do it all the way out,
Mm-hmm.
so you would just have to rationalize your denominator.
They're never going to do that.
Okay, so you're going to keep
Yeah.
the radical
Yeah.
in the denominator.
What I was looking to see if they had done in the back of the book, a minute ago I said factor as completely as possible. You may remember these problems from the first day of pre-calculus. They're my favorite problems in pre-calculus. We learned to write that factored as completely as possible. Now don't panic, because we're not fixing to do it today, but we'll do it later. What could I factor out of those two terms? A 1/3 and a t to the...
Negative 1.
You can take out the lowest exponent, and the lowest exponent's negative 2/3. So I'm just saying that's coming. It's not coming today, but it's coming right now. All we need to do is write it this way. One other thing, if the original problem has a radical in it, like back to what page were we on? 136. Back to page 136. If the original problem had a radical in it, like number 50, then the answer is probably going to be written with a radical in it.
Okay.
But on number 52, if the original problem just had exponents, the answer is usually written with just exponents.
All right.
There are rules of thumb here that, will apply most of the time and not apply on others. I will try to be very clear in the directions on the test to tell you how far I expect you to go. If I say find the derivative, factor as completely as possible, that's what you have to do. If I just say find the derivative, then there's probably several different looking right answers that I would count correct. All right, that was 52. 54 is not terribly much more exciting. Just tell me on 54 how I could write that first term as a constant times x to a power. 54.
Times x to the
2x to the
Two.
negative.
Ooh. I'm loving the iPod right now. Go away. iPad. My kids laugh at me. I don't know the difference in an iPod and an iPad and a text and an email. Okay, I can't make that go away. Yes, write that as 2x to the negative 1/3. That's annoying. Okay, 57 through 60. Say find the equation of the tangent line. Now that's a little more than we did on 33 through 40. 33 through 40 said step 1, find the derivative. Step 2, evaluate the derivative at this point. But now 57 through 60 are going one step beyond that. Let's go ahead and just pick a mega ugly one. 60 is mega ugly. Let me ask you something about 58 first. How could you write that as a constant times x to a power before you took the derivative? Beautiful. 2 times x to the negative 3/4. Have you done any calculus at that point?
No.
No, that's just the function, 2x to the negative 3/4. Then you would take the derivative. Then you would substitute 1 into the derivative. Then you would have a point and a slope, and you could use point slope form. So let's do number 60. Once again, if they only gave me an x coordinate for that point, how do I find the y coordinate? Substitute that x into the original function. What is sine of pi? 0. What's 1/2 e to the pi? 1/2 e to the pi. All right, so to get the answer in the back of the book, you're going to have to get comfortable with the exact answer, not your cute decimal approximation that you tried to give me on the test. All right. The directions say find the equation of the tangent line at that point. What does that mean do first? Clear your throat really loudly, and then what?
On the derivative.
All right, find the derivative. What's the derivative of sine t? Cosine t. And what's the derivative of 1/2 e to the t? 1/2 e to the t. So far, so good? Is that the equation of the tangent line? That's just the derivative. Now, here's another thing. I'm trying to teach you the words that you need in your head on test day. That's my goal from basic math all the way. Well, this is as far as I go. After Calculus 1, I won't be able to help you anymore. The last time I did Calculus 2 was 1987. So this is the end of the line for me. But I need to teach you the words that you need to think on the test. So the next thing you need to think is, now I need the slope of the tangent line. If I have a derivative and I have a point, how do I find the slope of the tangent line at that point?
Substitute the x into the
H prime.
Into the derivative. Substitute that x value into the derivative. I hear you whispering. What's cosine pi? -1. I don't think that's going to clean up real pretty. What is that? In words, what is it that I have found?
This thing
I have found the slope, and it's ugly, but I found it. But that's not all I was asked to find. I was asked to find the equation of the tangent line.
So you plug that into what's the formula?
Yep.
Oh, that's a big.
isn't that fun?
That's my slope. It's just ugly. Got to put it in the place of m. That's my m. This is my x1. This is my y1. Y minus y1 equals m times x minus x1. trying to think how they'll have the answer written. It's going to be ugly no matter what. But this is just a number. Let's figure out what that number's. Oh, I don't even. Okay, as wildly as I can guess, I'm going to say E is about what whole number? 3. Pi is about 3. So 3 to the 3 is about 27. Half of that's about 13 and a half, or if we're cheating here, let's just call it 14. And then negative 1 plus 14. That's about negative 13. You've got to play like it's a negative 13. You don't write a negative 13, but you...
Positive.
I'm sorry, what?
Positive.
It would be positive. You're absolutely right. It's about 13. It's somewhere between 13... I don't want to know exactly what it is, but that was a rough guess, about 13. You could distribute 13. That's what you would do next if that was just 13, right? Well, distribute the whole big ugly. That x minus that pi.
On that, you don't FOIL it, right?
You absolutely could, and you would get the same answer. I started to do that. I started to say this is a binomial times a binomial, let's just FOIL it. But when you FOIL, you're really multiplying both of these times that and both of these times that. Same thing. All right. I don't see any point in distributing the x. That's my slope, and I usually write my answer in the form y equals mx plus b.
Distribute the
I
negative.
just need to,
Distribute the negative. It'll cancel some terms.
But I can't ever say negative 1 plus this one is 0. Why can't I say that? That's not just negative 1, that's negative x. And negative x plus 1 wouldn't be like terms. All right. The only other thing I can think to do then, keep up with my m. That's the form y equals mx. And then let's go ahead and distribute the negative 1 and add 1/2 e to the pi to both sides. Not only should I distribute negative 1, I should distribute it negative 1 pi. Negative 1 pi times negative 1 is positive 1 pi. And negative 1 pi times that. Oh, just that.
Your conference is scheduled to end in 2 minutes.
I'm glad.
Times pi or...
Yeah, that's times pi. Normally I would just put the pi right here. I'm not exactly sure how the answer will be written in the back of the book, but one thing you're going to have to get comfortable with is different looking answers that mean the same thing.
They may distribute it now, or took out a half.
Yeah, they may have factored out a pi from the last 2 terms. I don't know. But this is exactly why on the first test I had the directions, give me the exact answer. Because that's how it's going to be written in the back of the book. That or something equivalent, not something with decimals.